Science is exciting. It's all about discovering how the universe we live in works. That's pretty important in itself, but it's by applying that knowledge that scientists come up with inventions to make people's lives longer, healthier, and better. Now you have the chance to find out more about science in an entirely new way on this brilliant video encyclopedia. It's based on the Oxford Children's Encyclopedia, the finest work of its type from the Oxford University Press, one of the world's greatest publishing houses. The video is really easy to use. You can look up information in exactly the same way as you would in a reference book, through the index. There's one printed on the inside of the video box. Find the topic you want in that, and you'll see two numbers next to it. The first number is the topic's reference number. Press fast forward and play at the same time, and wait until the reference number in the top left-hand corner of the screen changes to the one you want. Then stop your player and press play on its own. If your video player has a real-time counter, use the second number. Just press fast forward until the number on the display is the same as the second number in the index. Then press play. You have to make sure that your video player knows when to start counting, so make the display read 0 when our countdown reaches 0. 5, 4, 3, 2, 1, 0. Sometimes you'll see a screen that looks like this one. It gives a list of cross-references. This means that you can find out more about the topic you're watching if you look up the other topics on the list. You'll find that moving pictures on the video make understanding scientific ideas really easy. But books are just as important a source of information as video, so it's a good idea to use them both together. Fire is a chemical process. When certain gases combine with oxygen in the air, they produce lots of heat and tiny particles of carbon called soot. These tiny particles stream upwards glowing red or even white hot, and these are what we call flames. Whatever the material, it must be turned into a gas before it can burn. This applies to liquids like paraffin, as well as to solid fuels. The wick of a candle is coated with wax. If we light a candle, some of the wax boils and produces a gas which catches fire. The heat from this fire melts more wax, which in turn boils and produces more gas. This cycle of heat and the production of gas keeps the candle burning. Other fires work in a similar way. When people build coal fires, they usually put paper and wood at the bottom and the coal at the top. The paper is easy to light. A match makes it hot enough to give off a gas which catches fire. The burning paper makes the wood hot enough to give off a gas which also catches fire. And the wood burns long enough to get the coal hot. Once the fire is going, the burning gases from the coal make enough heat to produce more gas, and so it goes on. Fires normally need three things: fuel, heat, and oxygen. If one or more of these is missing, then there won't be a fire. For example, a fire blanket or a fire extinguisher will smother a fire by preventing the oxygen in the air from reaching it. We have made use of fire throughout most of our history. The Industrial Revolution of the 19th century was largely dependent on steam power, which was driven by fire. Many scientific developments would not have been possible without its energy. One very important early discovery was that fire could be used to work metals. At one time, fire was the only way people could produce the heat needed to cook food and keep warm in cold weather. Before the advent of electricity, fire also provided people with light in their gas and oil lamps. Nowadays, we still use fire to provide most of our power. The heat from burning coal, oil or gas is used to make the steam which turns the generators in power stations. The generators produce electricity, so that the energy from fire is now used in a safer and more controllable way.
People didn't invent flying. Insects were flying nearly 350 million years before the first person ever dreamed of taking to the air. Insects stay in the air by beating their wings very quickly. The first birds to develop the ability to fly didn't appear until about 200 million years after the first flying insects. Birds are well adapted for flying and have wings which are covered in feathers. To flap their wings, they have powerful muscles attached to a strong breastbone. To make flying easier, their bones are hollow so that their skeleton is light. The first bats appeared on the Earth about 50 million years ago. They are the only mammals that have wings and are capable of true flight. Their wings are made of skin stretched across their arm and leg bones. If you watch a bird taking off, you may see it jump into the wind and beat its wings. As the wing moves down, it pushes against the air, and this produces an upward force which can lift the bird's weight. The air is pushed backwards by the wing so that the bird moves forward. Air moving over a bird's wing creates lift. You can demonstrate this for yourself by blowing hard across the top of a small sheet of paper held level at one end. The paper rises slightly. This is because the air moving above the paper causes the pressure there to be less than the pressure below it, and so lift is created. A bird's wing is arched and thicker at the front than the back. This design makes the air travelling across the top of the wing move faster than the air below it. This creates lift in the same way that we discovered with the paper. It is this lift on the wing that keeps the bird in the sky. To make its body shape as smooth and streamlined as possible, a bird will tuck its legs up in flight. As well as its wings, a bird also uses its tail feathers to control the way it's going to fly. It was only by watching birds and experimenting with gliders that early inventors developed theories of flight, in particular that air moving over a wing can create lift. The result of these experiments is a wing shape called an aerofoil. Like a bird's wing, an aerofoil shape is thicker at the front than the back. Unlike birds' wings, however, aircraft wings cannot be flapped. Therefore, air must be kept flowing over them. Some aircraft achieve this by moving forwards using a propeller that turns very quickly. The engine works on the same principle as the one in a car, but is more powerful. With advances in technology, modern airliners are now powered by jet engines, which combine fuel with compressed air in combustion chambers to produce very hot gases which drive the aircraft forward. As the aircraft builds up speed along the runway, the air rushing over the wings creates the lift needed to raise it into the sky. An aircraft will stay airborne as long as it keeps moving forward fast enough for the lift created to be the same as or greater than its weight. Aircraft designers have to ensure that the shape of the plane is streamlined, like a bird in flight. This is because air moving quickly over a surface encounters a force which we call drag. We can observe drag in a wind tunnel. A non-streamlined shape produces a lot of drag. The aerofoil shape produces very little drag. The pilot controls the movement of the plane by using movable surfaces on the wings, the tail and the fin. Some of these are moved using a control column in front of the pilot's seat. To enable the aircraft to roll to the right or left, there are ailerons hinged on the back edge of the wings. These are connected in such a way that they move in opposite directions. The aircraft can be made to climb or dive using the two elevators on the tailplane. These move in the same direction. If they are lowered, air pushes against the undersurface and the plane will dive. The pilot operates the rudder by using foot pedals. The rudder is used to control left and right movements. The development of powered flight has had a tremendous impact on people's lives. A journey that may once have taken weeks can now be completed in a matter of hours.
Have you ever tried to hold a beach ball underwater? It's very difficult, isn't it? That's because there's pressure from the water that keeps trying to push the ball up. A beach ball is light enough for this upward water pressure to support its weight, so the ball floats. If you hold a brick underwater, there's an upward pressure on that as well. But the brick is too heavy for the water to support it, so the brick sinks. Something will float in water if each cubic centimetre weighs less than a cubic centimetre of water. This works for all other liquids and gases as well. Things float at different depths. Objects with more air in them float higher in the water. Stone will sink in water, and so will metal. But ice is light enough to float, and so is wood. Ships float in water even though they're made of metal. This is because the metal isn't solid. The inside of a ship consists mainly of air spaces which don't weigh very much. If you fill these spaces with metal or even water, the ship would sink. All ships have marks painted on the side of their hulls called plimsoll lines. During loading, they show how high the water level can be allowed to rise up the hull without the ship becoming unstable. There are some ships which are designed to travel underwater. These are called submarines. They submerge by filling up special tanks with water to weigh themselves down. To come to the surface again, they must become lighter, and to do this, they expel some of the water by blowing air back into the tanks. Some things are so light they can even float in air. Balloons can be filled with light gases such as helium, or simply with hot air like this one. This is because heating the air in a balloon makes it expand, and some air is pushed out of the hole at the bottom. This makes the balloon lighter, and so it floats. Remember that if anything is lighter than the liquid or air that surrounds it, then it will float.
All living things need food to stay alive, and that is why animals spend a lot of time either hunting for food or feeding. Green plants are different. They make their food by using the energy in sunlight to combine water, carbon dioxide gas, and mineral salts. This process is called photosynthesis, and by making their food through photosynthesis, plants store some of the sun's energy. All animals depend upon plants for their energy and are part of a food chain that begins with plants. The community of plants and animals that lives in a particular place is linked together by an interdependent need for energy and food. These links make up what we call food chains. In the garden, a plant may be eaten by a snail. Some of the sun's energy stored by the plant is passed on to the snail, which is a herbivore. If a bird then eats the snail, some of the energy is passed on to the bird, which is a carnivore. The bird may in turn be eaten by another carnivore, and so on. The plant, snail, bird and cat are links in a food chain which can be written like this. The arrows in the food chain always point from food to feeder. In real life, food chains are not simple straight lines, as each animal may form part of many food chains. This more complicated relationship is known as a food web. Many animals eat grass. These grass eaters may themselves be food for other animals, including birds and mammals. Notice that the food web shows a hierarchy. The carnivores at the top of this one, the fox, the kestrel and the human, are not killed for food by any other animals. As living things are linked together in food webs, it's easy to see why a change in the number of animals or plants in one part of the food web can affect all the other parts. So it's important that we try to preserve this delicate balance of nature.
When two surfaces rub against each other, a force called friction opposes movement. The amount of friction partly depends on the surfaces involved. A skater moves easily because there is little friction between ice and skates. There's more friction between our shoes and the floor. Friction makes it possible for us to walk. Without friction, we would slide about. Friction between rubber tires and the road allows vehicles to move. Friction between brake pads and wheels means we can slow and stop machines. Sometimes this can be wasteful. The force needed to overcome friction often creates heat, unwanted sounds, and wear and tear. When you ride a bike, some friction is helpful and some is a nuisance. Friction helps your hands grip the handlebars. Friction stops you when you put the brakes on. Friction helps your feet grip the pedals. Friction helps the tires grip the road. But friction is a nuisance because air friction slows you down. Friction also slows the pedals and the wheels. Spacecraft experience enormous heating when re-entering the Earth's atmosphere due to friction with the air. The front of the spacecraft has a special shield which heats to several thousand degrees centigrade. It then melts and boils off. This protects the spacecraft and crew from overheating. Lubricants such as oil provide a thin layer of liquid between surfaces and cut down friction. This can reduce wear in moving parts of machines. The bearings in machines often have a lubricant sealed inside. Oiling hinges stops them squeaking and makes them move easily. Friction can also be reduced by using a layer of air. This is why a hovercraft can move around so freely. The air cushion reduces contact between the surfaces to a minimum. Another way of reducing friction is by changing the surface. The special plastic used in non-stick pans is an example of this. Ball bearings reduce friction by changing a sliding action into a rolling one. Dragging a boat across a beach is difficult, but put it on wheels with bearings and it's much easier because friction has been reduced.
A fuel is a material that's used to provide heat or other forms of energy. Energy is vital to almost every human activity, from cooking to building a skyscraper. Nearly all fuels produce heat by being burned. Most of the world's energy comes from what we call fossil fuels, coal, oil, and natural gas, which are found in deposits underground. Fossil fuels are the remains of plants and animals that lived millions of years ago. These fuels won't last forever. It's estimated that the world's supply of oil will only last for between another 30 to 60 years, and coal for another 250 years. Fossil fuels will eventually run out, so there's an urgent need to develop something to replace them. At the present time, about 15% of the world's energy comes from burning wood. Wood is the main fuel for about 2 billion people, most of them living in developing countries. In some places, whole forests have been cut down for fuel or building materials. Unlike coal, oil or natural gas, new wood grows quite quickly so that stocks can be replenished. Unfortunately, not enough trees are being planted. Trees are being cut down faster than new ones can grow, causing severe environmental damage. At the moment, only 4% of the world's energy comes from sources other than wood and fossil fuels. As natural fuels become depleted, it seems likely that the demand for energy will be met by nuclear power. But nuclear power stations are very expensive, and if an accident occurs at one, there can be great dangers, as was shown by the fire at the Chernobyl reactor in the Soviet Union in 1986. Another problem is that getting rid of nuclear waste is very costly. And if it is mishandled, it can lead to serious pollution. If the process is carried out correctly, however, there should be no polluting products. There are some new fuels that could be developed. In many countries, household rubbish is buried in waste tips. In Britain, for example, 70 million tons of household rubbish are thrown away every year. As a fuel, or as a source of gas, this rubbish contains the same amount of energy as 20 million tons of coal. Some cities, including London, Amsterdam, Frankfurt and Paris, now have power stations that burn household rubbish to produce electricity. Many plants, such as maize, cassava and sugarcane, are rich in sugars. It's possible to collect these sugars and turn them into alcohol, which is a valuable concentrated fuel. Brazil is one country that has been trying to reduce its oil imports by growing these plants. Many Brazilian cars now use alcohol instead of petrol. A new way of producing electricity is by fuel cells. These cells change the chemical energy in hydrogen and oxygen into electrical energy. However, fuel cells are expensive and cannot deliver the same level of power as more traditional power stations. Some fuel cells are already used in spacecraft, including the Space Shuttle. Another way of making existing supplies of fuel last longer is to make engines more efficient. Petrol and diesel engines are being developed which are lighter in weight and which use fuel more efficiently. Further fuel economies can be made by improving the insulation of homes and factories. Insulation reduces heat loss and means that less fuel is needed to warm these buildings. Even switching off electric lights saves fuel.
We are surrounded by gases. The air we have to breathe to stay alive is a mixture of gases. Gases, unlike solids and liquids, spread out to fill any container in which they are placed. We can see this happen when we inflate a balloon. Many gases, like those in the air, are invisible and have no smell or taste. Gases from the air have many important uses in industry. Oxygen makes up 21% of the air, and large amounts of it are used in the making of steel from iron. Oxygen is blown through molten iron to burn up the impurities and turn it into steel. Sometimes oxygen is mixed with another gas called acetylene and burned. The oxyacetylene flame, as it's called, is so hot that it can melt steel. So it can be used for joining pieces of steel together, which is called welding, or it can be used to cut steel. Nitrogen makes up 78% of the air. Unlike oxygen, things can't burn in it. So it's often used to fill the containers where inflammable materials are stored. Another use of nitrogen is in the making of explosives. Here, explosives are used in a search for gas and oil deposits. Air also contains small amounts of other gases, including carbon dioxide. Carbon dioxide gas is used in fire extinguishers because, being heavier than air, it cuts off the oxygen and so helps put the fire out. Carbon dioxide gas is also used in making fizzy drinks by dissolving the gas in the drink under high pressure. When the drink is poured out, the carbon dioxide bubbles up. Another gas in air is helium. Helium is a very light gas. It doesn't burn, it's invisible, and it has no smell. Because it's so light, it's used to fill balloons and modern airships. At one time, hydrogen was used for airships, but unfortunately it burns too easily, and after a number of disasters it was considered too unsafe. Nowadays, hydrogen is mostly used in food manufacture, like making margarine. It's also used, together with nitrogen, in the manufacture of fertilizers. Neon and other rare gases are used to fill tubes which glow when electricity flows through them. They're used for making advertising signs that light up at night. Natural gas, the gas we burn in cookers and heaters, was formed, like oil, from the remains of plants and animals that lived millions of years ago. It's extracted from underground deposits and mainly consists of a gas called methane.
You may have heard of gravity as the pulling force that holds us all down onto the surface of the Earth. But it's not just the Earth that has gravity. Everything has a gravitational pull towards everything else. There's even a gravitational pull between people, though it's far too small to detect. The more massive the object, the larger the pull. The Earth, which is huge, has a very strong pull that drowns out the tiny pulls we have on each other. Gravity pulling us down gives us our weight. It makes us feel heavy. The Moon and some other planets have weaker gravitational pulls than the Earth, so we would weigh less on them. We weigh about 6 times as much on Earth as we would on the Moon. On a large planet, we would weigh more, even though we are exactly the same size. On the planet Jupiter, for example, we would weigh about 3 times as much as we do on Earth. As we move away from a planet, the pull gets weaker. However, being in orbit makes you feel weightless, even though the Earth is still pulling you. The pull of the Earth's gravity holds the Moon in its orbit circling round us, and the Sun's gravity keeps the Earth and the other planets in their orbits. Gravity also holds the Sun and 100,000 million other stars in a gigantic group called the galaxy. In fact, the Sun and the planets wouldn't exist at all if gravity hadn't pulled together particles of gas and dust to make them. When we balance one pencil across another, the point where they cross is the centre of gravity of the balancing pencil. All its weight seems to be concentrated at that point. If you add a small piece of moulding clay to one end, it will balance at a different point. The extra weight has moved the centre of gravity. Children using a seesaw are affected in the same way. If they were different weights, they would have to adjust their seating positions to keep the centre of gravity in the middle.
To understand the greenhouse effect, we need to understand how a greenhouse works. If you've ever been inside a greenhouse on a sunny day, you know it's hotter inside than outside. This is because radiant heat from the sun passes through the glass and warms the things inside. These lose heat by radiation, but the glass reflects some of this heat back into the greenhouse. In this way, the inside of the greenhouse warms up. We say that the glass traps the sun's heat. Some of the gases in the Earth's atmosphere act like the glass in a greenhouse. They trap the sun's heat and help keep the surface of the Earth warm. Without them, our world would be a much colder place. But this is now also causing a problem. In the world today, we are burning so much fuel and so many forests that we're putting larger and larger amounts of these greenhouse gases into the atmosphere. As a result, the Earth is slowly warming up. This is called the greenhouse effect. Unless the governments of the world take action, irreparable damage may be done to the atmosphere. If the Earth continues to warm at its present rate, the polar ice caps could melt and the sea level could rise by over 1 meter by the year 2030. If this happened, it would have disastrous effects worldwide, as the sea would flood large areas of low-lying land. Floods like this one in India would affect London and other major cities, and Egypt would lose up to 1/6 of its farmland. Our atmosphere is a mixture of gases. Of these, carbon dioxide is the main greenhouse gas. Animals, like ourselves, give out carbon dioxide when they breathe, whilst plants absorb carbon dioxide. In this way, animals and plants can keep the atmosphere in balance, and the amount of carbon dioxide stays the same. Our modern lifestyle is now upsetting the balance. When we burn fuels in vehicles and industrial processes, the exhaust gases put huge amounts of extra carbon dioxide into the atmosphere. In some countries, vast areas of tropical rainforest are being burnt to clear land for development. This is causing a problem. The burning is releasing more carbon dioxide, and the Earth is left with fewer plants to absorb the gas. There are several other greenhouse gases in the atmosphere. Methane is released by animal waste, swamps, paddy fields, and oil and gas rigs. Nitrous oxide comes from car exhausts and from chemical fertilizers used to increase crop production. Chlorofluorocarbons, or CFCs as they are called, have been used in fridges, aerosols and foam packaging. Amounts of CFCs in the atmosphere are small, but these gases are 10,000 times more effective than carbon dioxide at trapping heat. Special satellite pictures like this one over the South Pole show how CFCs are also damaging the ozone layer that surrounds the Earth. Scientists believe that the only way to slow the greenhouse effect is to produce less of the gases which cause it. We need to reduce our use of fuels such as oil, gas and coal, and find alternative ways of making power. These could be wind, hydroelectric, or tidal. We also need to build houses and offices which waste less heat, and transport systems which need fewer vehicles. Governments are already trying to reduce the use of CFCs, and by the end of the century, products should not contain them.
All living things are able to grow, but to do it they need food. Plants and animals get food in different ways. Plants need carbon dioxide gas from the air, water and mineral salts from the soil, and sunlight to make the food they need for growth. Animals need water too, but they also need many complicated foodstuffs like starches, proteins, fats and vitamins. These they can only get by feeding on the bodies of plants or other animals, or both. Although the foods used are different, the ways in which animals and plants grow are similar. To get bigger, living things make more cells. They change the food they take in into the material for new cells. These are formed when the cells that are already present grow and split into over and over again. This is called cell division. The faster this cell division goes on, the faster a plant or animal will grow. When a baby grows into a child and then eventually into an adult, this multiplication of many different types of cells occurs. Most of the organs of the body are made of cells that can increase in numbers and grow. Animals grow at different speeds at different times of their life. A human grows fastest as a baby. The rate slows down after that, except for a growth spurt during our teens. Different parts of the body also grow at different rates. For example, a baby's head grows more slowly than its legs and body after it's born. In plants, the cell division is concentrated at special growing points. These are usually at the tips of twigs or roots. In a bud, tiny new leaves and sections of stem are produced out of new cells. Root growth is produced by a rapid division of cells just behind the tip. They are then expanded to full size when the cells are filled like minute balloons with extra water. The time it takes for animals to reach the age at which they can breed varies enormously. Usually, the larger the animal is, the longer it takes to grow up. All these changes in growth are under careful control. The control is needed so that the final shape and size of the growing animal or plant is as it should be. Growth is controlled by hormones. These hormones are different in animals and plants, but generally have the same effect, regulating growth towards an adult which is able to breed.
Heat is a type of energy. You can see heat in action if you watch water being boiled. The still water becomes a furious bubbling liquid with steam rushing up and out of the pan. It's important to keep clear of the steam because it can destroy your skin and cause burns. If you put a lid on the pan, you'll see it jump up and down as the pressure from the steam tries to push it off. To understand what's happening when we heat something, we need to imagine what it's like inside that substance. Everything is made of very small particles like these atoms. In a solid, the particles are held very close together, but they vibrate backwards and forwards a little. When heated, the particles vibrate even more and begin to move away from each other. The solid melts into a liquid, where the particles can move more freely. With further heating, the particles move so quickly that they escape from each other. The liquid then becomes a gas. Heating a solid makes its particles move faster, rather like these peas. As the particles vibrate more vigorously, they push neighbouring particles further apart. The solid gets bigger, it expands. When bridges are made, small gaps are left between the long stretches of metal girders to allow space for expansion on hot days. Temperature and heat are not the same thing. The heat which would make a litre of water in a kettle boil at 100 degrees centigrade would only warm a bathful of water by a few degrees. The heat is spread out in the larger volume of bath water, and so the water is not as hot as the kettle. If the same amount of heat is concentrated in something very small, such as a tiny piece of metal, then it will make it very hot. It'll glow red and have a temperature of more than 700 degrees centigrade. Heat from a fire can travel to your skin in the same way as heat and light reach you from the sun. They're types of radiation and can travel through empty space. The radiation makes the particles in your skin move, and you feel warm. Have you ever felt the handle of a teaspoon after it's been standing in a hot cup of tea for a while? It gets very hot. This is because the particles of the spoon vibrate faster with the energy they get from the hot tea. They affect their neighbours and make them vibrate faster too. In this way, heat moves up the spoon. This movement of heat is called conduction. Metal conducts heat easily, so heat travels quickly along a metal spoon. Hot air rises because it expands and becomes lighter than the cool air around it. We can see this with a hot air balloon. The movement of hot air is called convection, and it's a very common method of heating houses. Convection also takes place in liquids. If we rub two sticks together fast enough, the heat produced can start a fire. We have to work hard to rub the sticks together because of the friction. The work we put into the rubbing produces the heat. If we pump up a bicycle tyre, the lower end of the pump and the tyre near the valve will feel warm. This is because work produces heat, and of course heat can do work. The study of the way that heat and work can be converted into each other is called thermodynamics. By understanding thermodynamics, we can build efficient factories and power stations.
If we take a photograph of an object or person, we get a two-dimensional picture. If we were to make a hologram of an object or person, we'd get a three-dimensional picture. This means that the picture stored in the hologram has depth, so we can see round the side of the object as though it was solid and really there. To make a hologram, we need the special single-colour light from a laser. The laser beam is split into two halves. One half shines on the object, which reflects the laser light. This light mixes with the other half of the beam, called the reference beam, making patterns called interference fringes. The hologram is a photograph of these patterns. It doesn't look anything like the original object. In fact, you can't see anything on the hologram plate. In order to see the picture stored in the hologram, we shine a beam of laser light on it, the same kind of light that was used to make it. Then, looking through the hologram, we see the object as though it was really there, although it may have only one colour, the colour of the laser light. We can see some holograms without using a laser, just by using ordinary light. As well as making beautiful pictures, holograms are used for testing in factories. They can show up small differences in things which should be exactly the same. Holography has been used on the space shuttle to show which of its protecting tiles have become loose. Some holograms work with reflected light. The holograms used on credit cards are like this. They give a 3D image, which is easy to see if we hold the card under a lamp. Holograms are put on credit cards because it makes them extremely difficult to forge.
The word laser is a short way of saying light amplification by stimulated emission of radiation. Lasers produce a narrow beam of light. The beam that lasers produce is much narrower than that of an ordinary lamp, and different in many other ways as well. The light has a single wavelength and is just one pure colour. Also, the light waves move exactly in time with each other. Scientists say that laser light is coherent or organised. Ordinary light is not coherent. It's a mixture of colours whose waves are sent out in disorganised bursts. Some lasers have crystal in them. Others have a tube containing gas or liquid. This is a diagram of a helium-neon gas laser. An electrical discharge or flash of bright light gives extra energy to the atoms in the laser material. The atoms lose this energy by giving out light. The effect builds up like this. A few atoms lose energy and send out light waves. These trigger other atoms into losing energy and sending out light waves, and so it goes on. The waves are all identical because they're all produced in exactly the same way in every atom. Mirrors at each end of the laser send the light to and fro, so that more and more atoms are triggered into sending out light. One of the mirrors is only partly reflecting. Light escapes through it either as a steady beam or as a sudden pulse, depending on the type of laser. The colour of the light depends on the laser material. Some lasers produce invisible infrared or ultraviolet radiation. Have you ever been in a supermarket and watched the checkout operator pass the goods over something that registers the price on the till? Each of the things we buy has a barcode on it, and the till uses lasers to read the barcodes to find out the price. Barcodes are made up of a pattern of black and white lines. The laser beam is reflected from the bars in pulses, which are changed into electrical signals. Compact disc players use the same idea. They pick up laser light reflected in pulses from the surface of the disc. Pulses of laser light can also be used to carry telephone signals long distances through optical fibers. Doctors use lasers to burn away birthmarks and some cancer cells. Eye surgery can be carried out with lasers, like reshaping the covering of the eye or cornea to correct nearsightedness. Doctors use lasers under controlled conditions. You should never look directly down a laser beam. It could damage your eyes and even leave you blind. Military lasers guide missiles to their targets. Factories use powerful lasers to cut through metal, glass, and even cloth for clothing. Also, the coherent light from lasers is used for making holograms.
Lenses, like the ones you see in spectacles, are specially shaped pieces of glass or plastic that bend a beam of light as it goes through them. There are two types of lens. A concave lens is at its thinnest in the middle. This kind of lens spreads out a beam of light. A convex lens is at its thickest in the middle. When a beam of light goes through a convex lens, it narrows down to a point as the lens focuses it. A convex lens can be used as a magnifying glass. If we hold one of these lenses above a newspaper, we can see that it makes the words look bigger. If we hold a concave lens over the same words, we'll see the words get smaller. If we hold a convex lens in front of a sheet of card facing a window, the lens makes a small upside-down picture of the window on the card. We call this picture an image. The convex lenses we use most often are the ones in our eyes. They make an image of what we're looking at inside our eyes. The image is upside down, but our brains are so used to that it seems normal. We can use lenses in spectacles to correct sight defects. A normal eye focuses light on the retina. A short-sighted eye focuses light in front of the retina. This is corrected with a concave lens. A long-sighted eye tries to focus beyond the retina. This is corrected with a convex lens. Lenses have many other uses in our lives. They are used in photography, where upside-down images, similar to the ones produced by our eyes, are recorded on film. Lenses are used in microscopes to magnify objects which are too small to be seen with our eyes. Lenses are used in binoculars to magnify things which are far away. Very distant things, like the planets in our solar system, can be seen by using a telescope.
Light is a kind of radiation travelling at very high speed. It comes from the sun or electric lights, or from hot or burning things like a fire or flame. Light travels through space and air at a speed of 299,000 kilometers per second. If we could travel at that speed, we could go round the world more than 7 times in a second. Light travels through transparent things like glass or water, but it's reflected off things that look solid like wood or clay. We call such things opaque. We see opaque objects when some of the reflected light enters our eyes. If there is no light, then we can't see anything. If there is light, then what we see depends on the nature of the light and the surfaces it contacts. Most surfaces reflect light in an irregular way, but some shiny surfaces, like mirrors, reflect light in a regular way. Tiny particles like dust or smoke scatter light in all directions. The bending of light as it passes from one material to another is called refraction. Light travels more slowly in water or glass than in air, so if something is seen in both at the same time, it will appear bent. The light from the sun is really a mixture of colours which we call a spectrum. The spectrum is a steady change of colour from red to violet. Beyond the red end of the spectrum is a type of radiation called infrared, which is invisible to the human eye. All warm things, including people, give off infrared. An infrared camera can pick up images even when it's too dark for an ordinary camera. Beyond the blue end of the spectrum is invisible ultraviolet radiation. Fluorescent paints and inks absorb the ultraviolet in daylight and change it into light which you can see. This is why they look so bright. Scientists call particles of light photons. Photons speed around, bouncing off things as they go. They travel in straight lines. Shadows show us that they travel in straight lines. If light could curve round things, it wouldn't cast shadows. Light waves are electric and magnetic ripples which can travel through space. Their wavelengths are so small that 1,000 of them would take up less than a millimetre. The different colours in the spectrum have different wavelengths. Red light waves are the longest and violet the shortest. Nowadays in Western countries most lighting is electric, but in the past people used lamps which burnt fat, oil or gas, and these are still used in many parts of the world. Modern electric light bulbs have a filament in them which glows white hot when electricity passes through. The filament is a tight coil of very thin tungsten wire. The glass bulb is filled with gases which stop the filament burning up.
Liquids are substances in a form which we can pour. They can become the shape of any container we put them in, but without a container, they flow everywhere. A liquid, like water, is made up of molecules. Water molecules look like this. They are so small that it would take billions to fill a teaspoon. When water is poured, its molecules flow over each other, rather like the tiny crystals do when we pour salt. Molecules attract each other. In a solid like ice, the attractions are so strong that the molecules are held firmly in place, but in a liquid, the attractions are much weaker. You can see this if we put a drop of water onto a plate. The water pulls itself into a round blob, but we can easily spread this out with our finger. In everyday life, we come across some strange liquids. Take tomato sauce. Have you ever thought why we shake the bottle? Tomato sauce is what scientists call a thixotropic liquid. It only flows easily when we start moving it about. Non-drip paint is another example of this. Only when we start to agitate it with a brush or a roller does it become a liquid which we can spread easily.
Living things are extremely varied. They can be large, like an elephant, or small, like a mosquito. They don't have to be animals. These trees are alive, and so are these plants. If we get food poisoning, it's because we have ingested bacteria, living organisms that are so small that we can only see them by using powerful microscopes. Living things live in all sorts of places and in many different ways, but they can all do several things which non-living things, such as rocks, water or air, can't do. All living things are able to grow for part or all of their lives. They're able to reproduce, in other words, to make a new generation of young, which grow up like their parents. Living things can react to changes in their surroundings. This amoeba can move away from unpleasant chemicals or towards a smell that might mean food. A plant may react to change in the weather by losing its leaves or opening its flowers. Big, complex animals can behave in still more complicated ways. This chameleon can change the color of its skin in order to fit in with its surroundings. Biologists have grouped all living things into kingdoms. Each kingdom includes those living things which lead their lives in a similar way. Most biologists agree on a 5-kingdom system of classification, and this diagram shows one way in which the groups have been arranged. One group is the prokaryotes, which include bacteria and blue-green algae. Another group are protozoa, which are animals with only one cell. And then there are fungi, plants, and animals with more than one cell. Living things are not always as easy to identify as you might think. Viruses can become active and multiply, but they can only do so inside the cells of other living things. Whether or not they are living things themselves is debatable.
Machines are devices that make work easier. Your home and school may have machines in them for washing clothes or preparing food. Some machines may be electronic, like a computer. But there are many machines so simple that we don't even notice them. We don't even call them machines. A door handle operating a latch is one. The hinged door itself is another. Without the hinge, it would be hard work moving a large piece of wood every time you wanted to go in or out of a room. However big and complicated a mechanical thing may look, most have in them one or more of the 5 simple machines: the lever, the wheel and axle, the ramp, the screw, and the pulley. Levers are the simplest of all machines. We use them to do jobs like lifting, pulling, and turning. They can help us lift heavy things. A spade is a lever. So are the teeth on a gear wheel. With a long lever resting on a pivot, we can lift a heavy weight we wouldn't be able to lift otherwise. Here we can see that the plank is a lever and the piece of wood is acting as a pivot. This makes it much easier to lift the weight. This diagram shows how the wheel and the axle make it possible to move loads along. The axle is the thing that holds the wheel onto something. A wheelchair is a good example of this. Disabled people use wheelchairs to get about. The long spokes act like levers. A ramp or slope makes it easy to lift something up a short height by moving forwards quite a long way. People in wheelchairs and mothers pushing babies in prams often need ramps to get in and out of doorways. A screw is really a long ramp wound up. It helps to move things from one place to another. Some car jacks use a screw. By turning it round, the weight of the car can be lifted higher and higher. This shows how a pulley is used to lift weights. Pulleys raise heavy things by making one downward pull equivalent to several upward pulls. Big, complicated pulley systems use lots of wheels. Using a pulley system, just one person can lift something as heavy as a car engine. Machines make it possible to put in a force at one place and get it out at another. They may change the direction of this force. For example, you may wind the handle of a whisk one way, but the beaters move in another direction. The simple machines we've just seen can be joined together to do a complicated job. In factories and workshops, machines do work that would take a long time to do by hand. The force to operate the machines is transmitted to them in different ways. One way of moving the force along is by gears. Meshing or locking together the teeth of 2 gear wheels makes all kinds of changes possible. Gears can be made to turn faster or slower and in different directions. Here, the small gear wheel turns the larger gear wheel more slowly, but with tremendous force. The effect is the same if you connect the wheels with a belt or chain, but now both wheels turn the same way. Belts and bands drive many kitchen machines, such as the washing machine and the tumble dryer. There are even tiny belts driving parts of your video recorder. If a belt has too much power, it'll slip. A chain overcomes this problem. It can't slip because it fits over teeth called sprockets on the gear wheels. Bicycles use chains in this way. The pedals turn a big gear wheel called a chain wheel. The chain turns a little gear wheel called a sprocket wheel, which is connected to the back wheel. On a bicycle, the back wheels may turn several times for each turn of the pedal. Machines are becoming more complex, and many work too fast for people to control. Electronic devices or robots are now used to control many machines. Modern factories may be run almost entirely by robots. They can assemble a car body and weld the pieces together with great accuracy. All that people need to do is to service and sometimes repair the robots.
There are probably lots of magnets in your house. They do things like hold the fridge door shut, or attract can tops to a can opener. There are lots of other magnets you can't even see. There are magnets in doorbells, there are magnets in television sets, And there are magnets in the electric motors of things like drills. The forces from a magnet seem to come from 2 points near its ends. These points are called the poles of the magnet. One is a north pole and the other is a south pole. If you hold 2 magnets with their north poles close, they push each other apart or repel each other. The same happens with 2 south poles. But a north pole and a south pole attract. Poles of the same kind repel, poles of opposite kinds attract. When a piece of iron or steel enters the magnetic field of a magnet, it becomes magnetized with poles that are opposite to those of the permanent magnet. This is why they're attracted to each other. Magnets attract some metals, but not all. They attract iron, nickel, cobalt, and most types of steel. But there are many metals they don't attract. These include copper, aluminium, brass, gold, tin, silver, and lead. Magnets attract tin cans because these are mainly steel. The tin is just a thin coating. Materials which are attracted to magnets can be made into magnets. If you put a steel needle next to a magnet, it too becomes a magnet. And it stays magnetized when you take the magnet away. An iron nail also becomes magnetized near a magnet, but it quickly loses its magnetism when the magnet is removed. Magnets which keep their magnetism are called permanent magnets. Most are made of steel, special metal mixtures, or materials called ferrites. They're made in the shapes of bars, horseshoes, and rings. Scientists think that in materials like iron and steel, each group of atoms is a tiny magnet. Normally, the atoms point in all directions, and their magnetic effects cancel. But when a material is magnetized, its atoms line up in the same direction, and it becomes one big magnet.
The Earth contains about 100 different elements, in other words, substances that aren't a mixture of anything else. More than 70 of these elements are metals, such as gold and copper. Pure metals are solids at room temperature. The one exception is mercury, a heavy silver-coloured metal which is liquid. You can see mercury in some thermometers. Mercury is shiny, and so too are other metals. Not all metals stay shiny when left in the air. Some metals, like aluminium, eventually become dull and tarnished because elements like oxygen make new chemical compounds on the surface of the metals. Iron and most steels will rust. Rust is a chemical substance called iron oxide. It is found whenever iron or steel comes into contact with air and water. Most metals are strong. Many can be bent without breaking. They can also be hammered or rolled into different shapes when hot and pulled out to form wires. Metals are good conductors of electricity, so they can be used to carry electricity in cables. Metals are also good conductors of heat, so they are used in things like irons. A few metals are found in the Earth in a pure state. These include platinum, copper, some silver, and also gold, which may form lumps called nuggets. We get most other metals from minerals known as ores. An ore is a mixture of a metal with other elements. There are 2 main ways of obtaining a metal from its ore. One of these is by a process called smelting. In this, the metal ore is heated in a furnace with plenty of carbon. The metal forms a liquid layer that can be poured off to cool. The other process is called electrolysis. In this, an electric current is passed through a molten mixture of ore or through ore that has been dissolved by an acid. The electric current separates the metal from its ore. Most metals we see every day are in fact mixtures. These mixtures are known as alloys. An alloy is quite different from the metals that make it up. This statue is made of bronze. Bronze is hard and strong, but it is actually made up of copper and tin, two metals that are weak and soft. Iron is one of the most important metals. It can be converted into the tough metal we call steel by taking out some of the carbon that makes cast iron very brittle. If chromium is added to steel, we have stainless steel, an alloy that doesn't rust. There are hundreds of different alloys, and more are invented every year. Aluminium is a soft metal, but it can make the strong, light alloys which we use in drink cans and kitchen foil. Aluminium is also used in high-voltage cables. Magnesium also makes strong, light alloys and is used along with aluminium and zinc in the manufacture of cars and aircraft. Pure magnesium burns with a brilliant white flame and is used in fireworks. Zinc is a dull-coloured metal which is used to coat steel to prevent it from rusting. Steel treated in this way is called galvanized steel. Nickel is a metal that doesn't tarnish or corrode easily and is magnetic. It's used in alloys with iron and steel to make them stronger and more resistant to corrosion. It's also used to make coins. There are metals which we can use in power generation. Uranium is a rare radioactive metal which is used to provide energy in nuclear reactors. We can also use metals to provide us with light. Tungsten is a strong, hard metal that has a high melting point. It is used for light bulb filaments. It is also used in special steels to make the cutting edges of saws and drills.